A warm welcome to all the students. Today we are going to start with the second unit, and in this second unit we are going to discuss non-deterministic finite automata. Now I have already discussed the difference between deterministic finite automata and non-deterministic finite automata. Okay, we will revisit it, but for now let us see the definition of non-deterministic finite automata. Non-deterministic finite automata, also called as NFA, is a phi tuple M equal to Q sigma Q naught A del, where Q is finite set of states, sigma is the input alphabet, Q naught is the start state such that Q naught is one of the states belong to Q, A is the set of all the final states or goal states such that that set of goal states is itself a subset of Q, and del is a transition function such that del can be written as a cross product of each state over each input, taking you to 2 raised to q possible states. Okay, now let us understand this transition function. So what is this difference between the transition function of NFA and that of DFA? Okay, now let us see this with an example. So let us first write transition function for DFA. Transition function for DFA is Q cross sigma, giving a single state Q. Whereas for NFA, the transition function is defined as del Q cross sigma, giving 2 raised to Q possibilities. To understand the difference between NFA and DFA, we'll have to go through the definition of DFA. So what did I say regarding DFA? Okay, suppose QK is one of the states out of n number of states in DFA, then it is called as DFA when from one state, on the reading one particular input, say A, you go to only one unique state, say QM. So the automata is called as deterministic finite automata if from a particular state, on the reading one particular input, say A, you go to exactly one unique state and no more states. That's why from Q, that is from any state, small q from Q, on reading any input sigma, okay, automata goes to exactly one unique state from set of states Q. Okay, so assume that the set of states in my diagram, let's say there are 2 states or maybe there are 3 states. Okay, I'll just write this further. Suppose Q naught is the start state of my automata that I have here. Okay, so what are the set of states in Q? Q naught, QK and QM. There are 3 states. What is input alphabet? Suppose input alphabet is A comma B. So the diagram or the automata is called as deterministic if from any state on reading one particular input, it should go to exactly one other unique state and not more than one state. Okay, so just to see the transition, okay, I will just draw this as a full DFA and then we will check. Suppose Q naught on B goes to QK, Q naught on A goes to itself, QK on A goes to QM, QK on B goes to itself, suppose. Okay, and QM on reading A or B, it remains to itself. So now when you find out the cross products, okay, when you find out the cross products, how do you find out cross product of Q and sigma? Okay, so the first transition here would be Q naught comma A. So first element from this set, first element from this set, then first element of this set, second element of this set. This is how we find cross product. So delta of first element from that first set and the second element of the set, transition. Okay, then second element of the first set and the first element of the second set, delta of qk comma a, and then delta of qk comma b, right? So I'm just finding out the cross product between q and sigma. Okay, so you get this particular transition 2, 3 and 4. Now what is left is the last element of the first set and first and second element of the second set. So for that, delta of qm comma a will be one transition, and delta of qm comma b will be the another transition. Okay, now let us find out. Now q naught on reading a transition from state q naught on reading a, where does it go? It goes to only one unique state called as q naught. Yes, in this diagram. Now q naught on reading b, where it goes? Q naught on reading b, it also goes to one unique state called as qk. Qk on reading a goes to qm, that's one unique state. Qk on reading b, it stays to qk itself, but still one unique state. And qm on reading a also, it remains to qm, and qm on reading b also remains to qm. So when you see these transitions, okay, now you will be able to deduce the meaning of this. Okay, from every state, you see this is one each state. Q naught is one state, qk is one state, qm is one state. So for each state in capital Q, on reading an input symbol either A or B, okay, transition takes you to exactly one unique state from Q. So Q naught happens to be one state from this Q. Qk happens to be one state from this Q, and so on. And that's why it's a DFA. So we said that a diagram or an automata is called as DFA if from each state in the automata, okay, for each state in Q in an automata, if on reading one particular symbol, it goes to only one unique other state. That is your DFA. Now in NFA, here the difference between transition function is, here I have written 2 raised to q. Okay, so what is NFA? NFA, the restriction of going to one unique other state, okay, this restriction is removed. So what is NFA? In NFA, from any state on reading the same input, it can go to n number of different states. Okay, for example, this diagram which is currently DFA, I would have called this as NFA if, okay, on reading A from Qk, it was also going to some other state, say Qn, or Q naught on A, it is going to Q naught as well as it can also go to Qk. So if I make these two changes, okay, 1 and 2, the diagram no longer it remains DFA, but now it is NFA. Okay, so after changing the diagram like this, let us see how will be the transitions. Okay, now you just see Q naught on reading A. Now it goes to Q naught as well as it goes to Qk. So on the right hand side, you don't get a unique state, you get two states. Agreed? Now Q naught on reading B, it goes to Qk itself. Qk on reading A, earlier it was going to only one state, but now I have drawn another state. So Qk on reading A now goes to two states, Qm and Qn. Qk on reading A goes to Qm and Qn also. Similarly, for the other states. So these are the changes. Okay. So in general, what is NFA? In NFA, from any state on reading one particular input, it can go to any number of states. Now how many states, maximum how many states it can go through? So automata is nothing but it's a graph. So if the number of states in the automata, it's say n, okay, if the total number of states in the automata is n, so suppose Q contains total n number of states, okay, then the number of transitions that can happen, okay, will be definitely 2 raised to n. Okay, which means that from any state on reading any input, okay, now NFA can make transition not to one unique state but 2 raised to q possible other states. If total number of states, okay, if total number of states in the automata are q, then it can make at the most 2 raised to q transitions. It can make transitions to at the most 2 raised to q states. Okay, and that's why I've written this. If total number of states in an automata is n, then the number of transitions that can happen in the automata is maximum 2 raised to n. So when I write here 2 raised to q, it does not mean it has to make 2 raised to q transition. It means it can make maximum 2 raised to q transitions and not more than that. Okay. Now in this diagram, the automata was making only 2 transitions, right? From qk on reading A, it was making 1 and 2 transitions. But it can also make more transitions. Okay. So how many states are there here? 1, 2, 3, 4. So in this diagram, since number of states are 4, maximum how many transitions can happen from qk on reading A? 2 raised to 4. Right? Which includes transitions made to other states as well as transitions made to itself and so on. Now, let us solve an example. Let us design an NFA for the following regular expression. Okay. Now, just to show you how easy it is to draw NFA, okay, I would also like to show you how can we design a equivalent DFA for the same regular expression. Okay, we have already solved this, but just to compare, first let us design a DFA for the given regular expression. Now, what is the minimum possible string here? AB. So minimum possible string will be AB. What are the other possible strings? You can have n number of A's ending with AB, or you can have n number of B's ending with AB, or you can have AB, AB and so on ending with AB, or you can have BA, BA and so on ending with AB. So these are the 4 primary possibilities. Then you can have combination of these two, that is some A's, some B's, some A's and so on ending with AB. Then you can make this ulta, some B's, some A's, some B's and so on ending with AB. Then you can have this combination, that is AB, BA, AB, BA and so on ending with AB. Or you can make this ulta, that is first BA then AB, first BA then AB and so on ending with AB. Okay, and then you can have the combination of these two. So let us just have these transitions. So what is the minimum possible string? AB. So from state q naught, okay, from state q naught, okay, on reading A it goes to q1, and on reading another B it goes to q2. So what I have drawn here is a DFA for minimum possible string. Agreed? I am just drawing this so that I can compare this DFA with the NFA that we will be drawing. Okay. Then let's see whether this string is accepted. N number of A's ending with AB. Now please note, while drawing DFA we were taking utmost care. Now since n number of A's should end with AB, you have AB. But the self loops of A, can I have a self loop over here? A ending with AB. If I have a self loop over here, okay, if I have a self loop over here, what will happen? Q0 on A, it would go to Q0 as well as it would go to Q1. That means on reading one input symbol, okay, it makes more than one transition. So then the diagram won't remain DFA, it will become NFA. Okay, so n number of A's ending with AB. So you cannot have a self loop here. Let's see whether we can have a self loop here. A, yes, then n number of A's ending with AB, accepted, right? Then n number of b's ending with AB. Now I can have a self loop here, single B, okay, n number of b's ending with AB, accepted. Then AB ending with AB, so A, B, then I can just have a loop here, A, B, ending with AB, accepted. Now BAB ending with AB, BA, ending with AB, accepted. Then some A's, some B's, some A's and so on. So sum is first B, and I can have another loop here to have more B's, second B, any more number of B's, A, n number of A's, B, n number of B's, and ending with AB. So A's, B's ending with AB. Then first B's, okay, I'm trying this string now. First B's, then some A's, then B's, some A's, and so on, ending with AB, accepted. Then ABBA, so AB, BA, BA, and so on, ending with AB, accepted. And BAAB, 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 and so on, ending with AB. So this is also accepted. So the DFA that we get is this DFA. Okay, so this is the required DFA. Let's start drawing the NFA. Now, minimum possible string we have already seen, it is AB. So from Q0 on reading A, we go to Q1, and then from Q1 on reading B, it goes to Q2. So minimum possible string is AB. So the NFA, the minimum possible NFA is AB. Now this part, it means any combination of A's and B's. So I can, since there is no restriction that on reading a particular symbol it should go to only one unique state, that restriction is not there. So I can simply have a self loop here, and I can say, okay, n number of A's ending with A, B. I could not do this in my DFA. Please note, I could not have a self loop over Q0 with A here, because it would have turned to NFA. But now definitely I can do it because it is anyways NFA. So AAA, n number of A's ending with AB, right? And on the same lines, I can just say A or B, n number of B's ending with AB. So then since this self loop has either A or B, it simply means that from Q0 on reading A or on reading B, or any combination of A and B, it always remains in Q0, and finally last AB is received like this. Okay, so this is the required NFA. Okay, now let us trace. Suppose the input string that is given to us, okay, suppose the input string that is given to us is, say, A, B, B, A, and B. Suppose this is the input string that is given to us, and let us now trace. Okay, so these are the states. Initially, your automata is in Q0 state. Agreed? Initially, the automata is in Q0 state. Now, from Q0 state, when first A is read in the input string, from Q0 on reading A, it can go to Q0 as well as it goes to Q1. So from Q0 on reading A, it goes to Q0 as well as it can go to Q1. There are two options. Okay, the automata will try out both the options and it will select the best path. Okay, now suppose Q0 is Q0 on reading A, suppose this loop is selected. Suppose you remain in Q0. Then next element that is encountered is B. So from Q0 on reading B, you still remain in Q0. Agreed? But suppose if on reading A from Q0, if it was going to Q1, then from Q1 on reading B, Now it would have gone to Q2. Now suppose we are in Q0. Then in Q0, if B is encountered, you remain in Q0 itself. But if we are in Q2, from Q2 on reading B, okay, if you are already in Q2, okay, then from Q2 on reading B, where do you go? So you are stuck here. Okay, you cannot proceed from this loop. Right? Now let us analyze this. So from Q0 on reading A, it was going to Q0 or it was going to Q1. Right? Then from Q0, suppose you remain in Q0, on reading B, you remain in Q0. On reading another B, you remain in Q0. Correct? Now this path is stuck, so you cannot proceed from it. Now let's come here. Now you are already in Q0, and from Q0 on reading A, what will happen? Either you go to Q0 or you go to Q1. Any one of this. Now suppose we retain this path, that is Q0 on A, you remain in Q0. Then on reading A, from Q0 on reading A, again there are two possibilities. From Q0 on reading next A, there are two possibilities. Either you remain in Q0 or you go to Q1. Either you remain in Q0 or you go to. You are in Q1. You are already in Q1. From Q1 on reading A, is there any transition? No. So that means this path here is also stuck. Agreed? So now we are having only these two alternatives. So Q0, from Q0 on reading A, either you can remain in Q0 or you can go to Q1. Suppose you remain in Q0, then from Q0 on reading B, you will still remain in Q0. Now observe here, the input string is over. Right? Are you in the final state? Is Q0 the final state? No. So that means with this path here, you have not got any solution. But with this, automata will not finally say that the given input string is rejected since you have not reached the final state, because there is another branch yet to be explored, right? So with this branch, it is not fruitful. But now still this is left. So suppose you are in Q1. Okay, instead of Q0 on reading A, suppose you are in Q1. Now from Q1 on reading B, where do you go? So from Q1 on reading B, you go to Q2. See that there is nothing else remaining to be read, and you also have reached the final state. Is it not? So the NFA, okay, it concludes that the goal has been found. Okay, that means this string is accepted. And the path is this. The path that is considered is this. Okay, so this will be the path that will be considered. So what NFA will do is NFA will try out all the possibilities, all the possible tricks, and in turn, when you traverse the input string, this okay, it looks like a tree. So it will try out each and every branch, and finally, if it finds one particular path that is fruitful, that takes you to the solution, okay, it will say that the given input string is accepted. Okay, and that's why it is called as non-deterministic, because there is no one direction, there is no one perfect path that have to be traversed to get the answer. What non-determinism does, it tries out all the possible paths, and even if one path gives you the answer, you say the given string is accepted. This is your non-determinism. Finally, let us draw a transition table. Transition table is just a table, okay, it's a tabular representation showing you the states and the other states where the transition happens on reading the inputs. So we have states on the columns, okay, each column depicts a each row depicts a different state, and each column is a different input. So let's list which are the states. Q0 is a state, Since it's a start state, I will use an arrow here to indicate that it's a start state. What other states is there in the NFA? Q1. And since Q2 is a final state, I will write Q2 and I will write a star here. That star means it's a final state. Arrow means it's an initial state. So let us now see the transition from Q0 on reading A. From Q0 on reading A, it goes to two states, right? It goes to Q0 as well as it goes to Q1. So here you will have set, that is Q0 comma Q1. From Q0 on reading B, it goes to only one state, that is Q0. So only one state I will write here. Now from Q1 on reading A, there is no transition. So when there is no transition, I will write null, phi. From Q1 on reading B, it goes to Q2. So from Q1 on reading B, it goes to only one state, that is Q2. Similarly, from Q2, there is no transition defined on reading A as well as B. So here it will be null and here also it will be null. So this is how we draw a NFA. In this problem, we are asked to design an NFA for the given regular expression. Now, before I solve this problem, I would like to tell you that there are some regular expressions for which DFAs are very complicated to draw. Rather, NFAs are very simple. Let's begin with this. Minimum possible string is single zero. So, starting with Q0 state, initial state, on reading a single zero, it goes to Q1, and Q1 is made as the final state. So this is how single zero is accepted. Now 1 should be accepted. So from Q0 on reading 1, I go to Q2, and on reading another 1, I can come back to Q0. So this is a 1 1 1 1, any number of pair of ones, not single one but the pair. 1 1 first pair, 1 1 second pair, 1 1 third pair. Any pairs of ones finally ending with 0 will be also accepted. Similarly 1 1 0 contains a pair of ones followed with 0. This is also should be accepted. Now since it is NFA, there is actually no restriction on how many transitions are made from a particular state on reading the same input. So I can very well create like this. I can very well create another state over here. I can just name it as Q3 or something like that, and I can say from Q0 on reading 1, I go to Q3. From Q3 on reading another 1, I may go to Q4. And from Q4 on reading that last 0, I come to Q0. That from Q0 on reading single 1, it makes one transition here, and from the same state on reading the same one, it makes another transition here. As you can see, this is the required NFA. So if somebody gives you a string, say 1 1, okay, 1 1 0, 1 1, and so on, ending with 0. Okay, it would be very simple. 1 1, it will take you to Q0. Then 1 1 0, again to Q0. 1 1, then 1 1 0, and finally ending with 0. Similarly, string like 1 1 0, 1 1 0, 1 1 0, ending with 0 will be also accepted. 1 1 0, 1 1 0, 1 1 0, ending with 0 will be accepted. So there are some areas wherein drawing DFA can become a very complicated matter, or DFA for a particular problem can be very complicated. Rather, the NFA for the same problem could be simpler. So this is one such example. So friends, that's it for today's lecture. In the next lecture, we are going to see the extended transition function for the NFA. Thank you.